Alright, so in this video lesson, we are going to study about the surface integrals right here. Okay. Alright, so now getting into that kind of study for specifically surface integrals right here, then we have to begin, at least in my teaching philosophy, let's begin with learning about how to calculate or how to find the surface integral for a scalar function. So what's highlighted here is that we're learning first how to calculate the surface integral for a scalar function. Okay, and so before we can get really further into this particular subtopic about all of the surface integrals here, and specifically surface integral for a scalar function, I want to make a comment that this video lesson must be viewed after you have already learned from my other lessons about how we calculate surface areas for parametric surfaces, okay, for space parametric surfaces. Okay, so in case you haven't learned about that primary skill about how you can calculate the surface area from a surface that's parameterized parametrically, then I highly recommend to watch and learn from that video lesson of mine before we proceed into this. All right, but other than that, assuming that you have met all the prerequisites, let's get in and find out how we can calculate the surface integral for a scalar function, and even we're gonna learn what it is. Okay, we want to find out what it is. All right, so now with the idea of surface integral for a scalar function, let me begin with something like this. And so strictly as I have mentioned earlier, this lesson is best viewed after you have already viewed and learned from my video lessons about how I explained on how you calculate area on the surface area on a parametric surface. Okay, and so think about that we have a surface. Okay, so with that idea that you have learned in mind about calculating the area of a surface, the surface area in general, then when you're looking at a space surface like this, I'm going to just simply pick a point. Just simply pick that one point on the surface itself. And think about that one point right here. If I really try to zoom in, so right now looking from afar, it's simply just one point, one infinitesimally small point on the surface. But now think about if we're using like a magnifying glass and look really closely and zoom it into a very extreme level of zoom, like magnifying it up, then even a one point there, one infinitesimally small point can be seen in a very extreme zoom level, can be seen as another subpartition of our surface here. And so we can have so many, see, I can draw just simply one stripe like that along my surface right here, and there are infinitely many of those little surfaces like that. Okay, so what I said earlier is it's composed of infinitely many of those little subpartitions, and they keep getting smaller and smaller. And so this idea is thoroughly discussed in my video lesson about how you calculate area of a space surface. And then, so now with this subsection that we zoomed in right here from that point right, on the surface right here, that we zoom it in, we realize that there's still a noticeable subsection of my surface here. And so now, once again, picking up from that idea, then this subsection right here, we call that it's a ds. Okay, it's a small, tiny area unit. I call that an infinitesimally small area unit on that surface right here, on that space surface. And regardless, I said something about parametrically described, but even this argument here is even completely independent with whether with how your surface is being described. You can describe your surface parametrically, or you can describe your surface as a function of two variables. Okay, so but in the end, any surface here, we pick simply any point, and that point, when we really zoom it in, or when we really magnify it out, we realize what we have here is a subsection as an infinitesimally small area unit. Okay, and so the ultimate idea from that lesson when I was teaching about finding area or the surface area or area of a surface like this, of a space surface over a domain, then think about that in that lessons about finding area of a surface, then if we're producing a double integral, and in my term now, with anyone studying with me, I keep recommending my students to think of an integral, any kind of integral, as accumulation. So here being a double integral, let's think about to obtain this area. So a little bit connecting back to our surface area lesson, then to obtain the total surface area here, then we're taking a total accumulation of all of those sub-area units. So there's one sub-area units, all of those are lining up along these different grids here. There are infinitely many grids along one way and along the other way. And that's why it's a double integral, it's a double accumulation of all of those the sub-area units, infinitesimally small sub-area units, and then accumulating that all over our, so S here is indicating some description that indicates the entire, whatever limited or the spread out space surface. So this formula we have seen before is to get the area of S, of that surface S right here. Okay. And so it is important that I mentioned that briefly, but of course we're not going to spend the whole lecture here, the whole lesson here to just study about how you can calculate surface area, because we've done that before prior to this lesson. But now the idea now is that think about it. Back in the old days, back at that earlier lessons when I was just calculating area, then the accumulation ends right here. When we're creating that double accumulation, that double integral, then we produce for ourselves and you know, accumulating all of those ds. So think of the ds here as a sub area units. Okay, sub area units, and we're accumulating all of those sub area units. That's why we're ending up with the total area. But so now think of that idea right there. That was what we've done before. But now at this point, we're doing a little more extra work. So now think about for each ds. For each ds, and it's a capital S, I intend to write capital S and capital S, all of that. So for each of the ds here, think about that ds, or pick a different ds right here, right? For each of the ds right here, in a zoom magnified level right there. This is a ds, another ds right here. So on each ds, this is what I'm doing. For each ds, okay, I am not only just, so it's an area, but now aside from that area, I'm going to take the product of that with some function value. So the function here is a scalar function f of x, y, z. And so I have to take a quick remark right here. This function here got to be a function of 3 variables. It's because, you know, being a point on, or being any point on that surface right here, it's you know, it's a 3 coordinates point. Okay, it's a point with 3 coordinates. And so now I'm talking about, we are going to multiply the area on each subunit right here with a function value, some scalar function output value at that given point. So why is it only at a given point? Even though I talked about, we magnified it out into a very extreme level so that we can recognize a noticeable sub-area units. But in the end, looking from afar, it's a very small distance. I mean, it's a very small area unit, to the point that it's just the whole area shrink, the whole sub-area unit shrink to just one point itself, and that point itself is simply just the point x, y, z. And that's the idea. And so checking this product at this point will get us some value, not only just the area. So the area is before we multiply with the function value, but now on top of each area, we multiply with a function value, some kind of function. Okay? And so now we got some, so this value here now, the function's value at each point, f of x, y, z, multiplied with each sub-area units here. That's only at one sub-area unit. But now I'm talking about on the entire surface, we have infinitely many points. And so now we're going to accumulate all of these quantities. We have infinitely many of these quantities throughout the entire surface. So each point right here, you can magnify that out and see that there's a ds right there as an area. And then in that area, there's a sum function that changes value depending on each different little sub area. That's why taking this product now, and then we're gonna do a double accumulation all around that throughout the entire surface S. So for easy purpose, let's line them up into lines like this, right? So on each line right here, we got infinitely many points like that. Each of those points is a ds, and then we're accumulating all of those, and that's why it has to be a double integral. And then accumulating all of those products right there, okay, throughout the entire surface S. Okay, so now, ladies and gentlemen, we have just now produced round 7 integral. Okay, it's not exactly the areas, the surface area that we've done back in the days anymore. Okay, but this is some kind of double integral over a space surface. Okay, and this double integral right here, what we have is a scalar function multiplied with each of our sub-units, sub-area units ds right here. And so, yes, ladies and gentlemen, we call this double integral in the setup that I was pointing out right here. This double integral is regarded as this is a surface because it was taken over a surface, a space surface. So it's a surface integral. Okay, that's what it is. It's a surface integral, a double accumulation. It's a surface integral of the scalar function. F of x, comma y, comma z. And then we're taking that surface integral over the surface S right here. And S was that entire surface that I drew earlier, and just now I had to erase. Now I can quickly draw that line again, draw that surface again. Okay? So there are infinitely many grids right there. And right now when I'm drawing, I'm not skilled enough to draw very tightly closed grids, but the idea is that there are infinitely many closed grids, so that each point on the grids right there has to be an infinitesimally small sub areas, and on top of each sub area units, we multiply the sub area units with a function, scalar function value. And so the idea of the scalar function value is that it's changing depending on whichever point that we're at, depending on each sub area units right there. Okay, so maybe at this sub area units we have some lower function value, and then when we are at that other sub area units we add some higher function value, and then maybe at some other sub area units we're at some even negative function value, and then we're accumulating all of those. We take the products between the function's value and the sub area units, and then we're accumulating all of those as a double accumulation in two directions like that. And that's how we produce this, what's so-called the surface integral. Okay, of the scalar function f of x comma y comma z over the space the surface S. All right, and so that begins the idea of what a surface integral of a scalar function is all about. Okay, but now we definitely need to go even further. So the primary idea is here, the primary setup is here. That's all it needs. Okay. But now, of course, we're just staring at some setup like this. It's not getting us anywhere. So we got to get really into understanding a little further so that we will have real access to how we can do a calculation, an actual calculation. Okay? And so in that way, now to make things a little more systematic, okay? Back in my lecture about surface area, then for any space surface S, okay? There are two primary ways of describing a space surface. You can either describe this as, we can describe S as a function, z equals f of x comma y. We can express, or we can think of this space surface here as a surface that came out from the graph of a two variable function. That's one way of how you're seeing it. Or S can be the same physical surface in space. S can be described parametrically. Okay, parametrically as some vector value function of two variables, r of u comma v, or s comma t, or the point is it's a vector value function of two variables dependent on two variables, where the x component is some function of two variables, u comma v, okay? The y component, so each point that there, okay, from the origin, okay, each point on the surface makes a vector with the origin, right, pointing out, and then that vector there is dependent on the x, the y, the z components of that vector dependent on two variables, two parameters u and v. Okay. Right. So there are two different ways how we can describe a space or surface. And so now in this particular lesson about surface integral, we are going to specifically going further and deeper into the when S has a parameterization, when S is specifically described parametrically, okay, as a vector value function dependent on two variables. Okay, so we are getting into that direction a lot more often than seeing S as a function z equals f of x comma y. All right. So in that way, now as I have explained, then with S being parameterized, with some parameterization, let's say S here described parametrically by some vector value function of two variables u comma v. Okay. Then my point and my intention here is that think about we already had a parameterization, and I'm not bringing up that kind of problem. I'm not yet bringing up that kind of problem where we have to find a parameterization ourselves yet for that describe a space surface. So right now, just say that, hey, assuming that we know that we have a parameterization given for our space surface, okay, and then whatever that is, right, described as some vector value function or of u comma v. All right. So with that idea, keeping that in mind, then again, connecting that with that lesson we have learned earlier, because a lot of things remains exactly the same. So if S here is parametrically defined or parametrically described as a vector value function dependent on u and v, then back to that surface integral. The surface integral currently looks like this. Okay, it's a surface integral, a double integral over the region whatever that defines our surface S right here, over the whole surface S. Some function f of x comma y comma z, okay, with ds. And so I keep bringing back that lessons about the surface area because the way we understand this ds is exactly the same of the way how we learned about the ds back in the video lecture where I taught how to calculate surface area. Okay, the ds has exact meaning. And so in that way, again, one more time, I'm asking you to think back, assuming that you have already learned from that video lesson how to calculate surface area. Then the ds right here on its own has an interpretation. The ds right here has an explanation for that. ds can be re-expressed as the magnitude of our r sub u cross with r sub v. The magnitude of our r sub u cross r sub v multiplied with dA. Right? And so to save your time for viewers here, instead of watching through all of the lengthy explanation that I have already given in my surface area lesson, then I just recommend that in case you don't remember this, you can refer back to my video lessons about how I explained about how I derived this ds right here as the magnitude of ru cross rv right here, the magnitude, okay, and multiply with dA. All right, and then notice, keep in mind that the dA now can be, and all of that explanation is given in the video lessons about surface area, but the dA here is just simply either the du dv, and eventually we'll get to that, or could be a dv, du. It's just a matter of the order of integration for a double integral, because now, so if you notice at this point, a surface area is a double integral, and now a surface integral in general on a scalar function is also a double integral. Okay, so it has that real close relationship there between the two. All right. And so now allow me to advance even a little further. So let me explain a little bit. See here that R here is a vector value function, and it's, formally speaking, the x component of this vector is a function, or any x value, or the x coordinates of any point on that plane can be described as a function of u and v. Any point x, y, z. Okay? And so the y components of any point on that space surface can be expressed as a function of u and v. All right? And then the z coordinates of any point on that space surface can also be expressed as a function of two variables u and v. And that's formally how it's understood. And so in that way, R sub u right here, it's a vector, but it's the vector that came out from the partial derivative for each one of these components in respect to the u variable. Because see, each one of our component values here is a function of two variables u and v. And so as a quick reminder, R sub u means the partial derivative of our vector value function in respect to u. So that means it's xu for short, yu, and zu. It's partial derivative of these three functions right here in respect to u. That's what it is. And then, so it's a vector. And so now, similarly, Rv right here, R sub v, the partial derivative of our vector value function in respect to v, that must be xv, y sub v, and z sub v. All right. And so that's the meaning of these two vectors. And so now when we take their cross products, think about that. We take their cross product and calculate the magnitude, and that magnitude multiplied with dA, that equals ds. And so how it arrives there, I have all of those details explained in the video lessons about how to calculate a surface area. Okay, but so now we're taking just this known information. We just simply take this known information and use that for our surface integral in general on a scalar function. All right, and again, notice each one of our point x, y, z at coordinates x, y, z can be expressed as a vector value function depending on the u, v. So eventually, in the next step, think about this. I'm going to substitute each component here into my x, y, and z variable of the function of the scalar function here. All right, so now let's move on. All right, and so in that case right here, in that way, how I explained earlier when I was on the other board, then with our current surface integral over the whole surface S right here, generally for some function, for some scalar function, f of x, y, z in respect to S right here, right? That can be rewritten as a double integral. So now for my function, each of the x and y and z components right here can be written as, so the x now can be substituted by whatever the x components in our vector value function. So it's x, u, v. So eventually x will be replaced, will be substituted by some function in terms of u and v that came out from our parametric equations. The y variable in our equation here also will get substituted by some function y, of u, v, and the same way with the z variable, right? It has to be some function of u, v, and that completes our function. So our scalar function f right here will be re-expressed as some function only in terms of v and u and v at the end. And then with all that, we multiply, and I'm running out of space here, so I have to write this in the bottom line, but technically it's the next part over. So it's in products with, and not a dot product, just in products with the magnitude of RU cross RV, okay, dA. And that's how we write this. All right, and now it's still over the whole S right here. But then at this point, let's make a major switch right here. Now we redefine, now we have substituted U and V, and we redefine the meaning of our X and Y and Z right here. So think about it. The function f now is only dependent on U and V. And U and V, right from this parametric description right here, of course I didn't write it here, but anytime you have a parametric description, it always comes with some domain for U and some domain for V right there, or a general 2D domain for both U and V. Okay, and so normally it's like U is in between some values, some two values, and B and V comes between some two values, C and D right there, for example, or maybe even between curves and curves, a general domain right there. And that's what it is for, that's what I call a domain where U and V parameters take values in. Okay, and so in that way right here, this expression here, this surface integral can be re-expressed as a double integral over some domain. And I will explain what that domain is, some domain D, where, and a shorter version of this can be written as f of, see, why wasting so much effort of, this is just to make it real clear for audience, but more generally many textbooks, authors out there writing this as the function at any general R point at U comma V. Okay, because R is a vector value function, but also indicating it's a point at any random point, at any point on the surface. Okay, so the function value at any point on the surface represented by the function R. That's what it is. And then we multiply with the magnitude of RV, I mean RU cross RV magnitude times dA. Okay, and so this is, no matter what I do, this part right here is always a scalar value. That's a scalar function, of course. And then the differential dA right here is also a scalar quantity. And now this is purely a double integral, where D right here, now right now I'm just giving a generality, a general understanding. So all I can say is D is the domain of all pairs U comma V, okay, for S, for the surface S that parametrically described by some function of U, some vector value function of U comma V. All right, so this formula, ladies and gentlemen, will give us access to the real actual calculation of our surface integral for any the scalar function. All right, I have mentioned this throughout what I was going over earlier, but now it's worth it to really nail it down right here, but as a couple of remarks. Okay. So the function f that we're doing here, okay, the scalar function f, must be, okay, a function of 3 variables. All right, that's one remark. Very important to understand. Okay. Now taking the integral is a double integral, but the function itself has to be the scalar function has to be a function of 3 variables. Okay. The surface integral that we're doing, or any surface integral, okay, and the surface integral must be, in the way it is, must be a double integral. Okay, it's got to be the way it is for them. All right, and then after taking these 2 remarks right here, now we are ready for pushing it into one example to demonstrate how that we can do the calculation. All right, so that is our first problem right here. We want to evaluate a surface integral for the function, the scalar function here is x squared, right, with that ds right here. So this is just a standard expression indicating this is a surface integral for our scalar function here in respect to s, in respect to units area, subunits area on the surface. And the surface S here is a unit sphere with that equation like that. All right, so now you can take your time writing down the problem like that before I proceed. All right, so assuming that you have had some time copying it down, including taking some the pause time like that to write down the problem. So now when I was giving the explanation, then I made it seems like the parameterization will always be given. But right here, in this first example, let me also bring in some experience for you of how you can come up with your own the parameterization. So a unit sphere is standard enough that a lot of people know, right? That for any unit sphere with this equation right here, we can parametrically describe that as a vector value function. So R of u comma v. So I'm halfway. I'm halfway the teaching you that how we can calculate that with a supposedly given the parameterization, but also I'm reminding you how you can come up with your own parameterization for a space surface as well. So it's not that easily given, right? But we know that it's a unit sphere right here with that equation. So sphere on standard has a parameterization as a function, as a vector value function of two variables, u comma v here being written as. So now we got its radius 1, so it's going to be sine of u times cosine of v. That's the x component, okay? And we can write sine of u times sine of v. Okay, that's the y component, and then the z component here is simply cosine of u. Right. So that's one standard parameterization. And that's why I was saying, it's mostly given because everybody knows. But in case you haven't known this, it's okay. I just showed you that. Okay, and then you can also put that into your little pockets reference about the different parameterization for different space surface. A sphere itself here is a surface. Now this surface here takes parameter values u going anywhere from 0 to pi, and v, this other parameter takes values from 0 to 2 pi. So this is that domain I was talking about right here. So back on this final formula where it gives us access to the actual calculation. The D here in my explanation earlier, it's the domain of u comma v for our surface right here. So our surface in this case being the sphere. And so parametrically it's described like that. So we have a given parameterization. And so now this here right here gives us the domain of our sphere right there, of our surface. All right, so this is how we begin into that. All right, so now with this given parameterization right there, we kind of found it. We also kind of think of that as some known information. That's what I meant by with S being parameterized with some given parameterization. And so now, as far as the calculation done, doing the calculation, we will need R sub u and R sub v. So let's find it. Okay, so R sub u here will come out being, and anyone viewing this lesson should be fluent enough with all of those skills about taking partial derivatives and all that. And so now I'm looking at cosine of u times cosine of v. Okay, well, for the x component, and then now cosine of u again times sine of v. Okay, and the last one here is a negative sine of u. All right, so that's R of u, and then my R of v here will be minus sine of u sine of v, partial derivative of R in respect to v. And now I have sine of u times cosine of v, and the last one here goes to a 0 because it's completely in terms of u only. All right, so that's my Ru and Rv right out from this parameterization. Okay, and so in that way right here, my board space is getting tight, but after getting, it's just a process, right? After getting the two partial derivatives of our vector value function here, we are going to take the cross product. So now I'm going to go Ru cross Rv. Okay, Ru cross Rv, and then after that, let's do two work at once. Right? So I'm going to take the magnitude of our RU cross RV right here. And so again, I don't have enough board space to write all of that work, but anyone viewing this lesson as a prerequisite should be able to fluently calculate the cross product of any two given vectors and then find the magnitude afterwards. So the order of operation here is that first you got to calculate the cross product and then take the magnitude. So you can double check your work with my answer here, but it should come out being sine of u right here. So this is the magnitude for our cross product of the tangential vectors. And so the important things about this is that these two, each one of these this is a tangent vector along the u direction, okay? And this is a tangent vector along the v parameter, right there. Along the u parameter, the tangent vector along the u parameter, the tangent vector along the v parameter. And that's why we're taking the cross product, okay? And then taking the magnitude of that. So we get a scalar value sine of u, all right? And that's how it's done. So for now, up to this step right here. So all right, so now we are ready to advance further with our double integral, with our surface integral from the beginning. S of the function x squared times ds. That's just a general indication of a surface integral. And now we can rewrite this as, so x here in the parameterization, x is simply just sine of u times cosine of v. So now we're going to square that because it's x squared. All right, and then we take the double integral. Right? And then the dA earlier can now be expressed as, because this is now sine of u that came out from the magnitude of our RU. So this part right here is the magnitude of RU cross RV that we have calculated earlier from the other board. And so now we need to also multiply with some dA right here over the domain of our two parameter values u and v. So this is already taking us a lot further and closer to the being able to get the calculation done like that. All right, and so now just realize again that I had it written down earlier on the other board that u takes value anywhere from 0 to pi, and v take values anywhere from 0 to 2 pi. So this integral right here, all of a sudden we realize it's now just simply like any other ordinary double integral of two variables, functions of two variables, including that sine of u and sine of u squared and cosine of u of v squared right here. And then with your the parameter values taking values in between 0 and pi for u, and then from 0 to 2 pi for v right here. Now we can rewrite this complete integral as the following. So this is really our access point that allows us to do the calculation. And then with that information that I just now reminded everyone, then now it becomes okay. So it's just me, I like to write the du first, integrate in respect to u first. And so now I'll go from 0 to pi, right? And let's clean up our expression right here. Now it gives me sine cube of u times cosine square of v. And now with that function here, I'm going to integrate in respect to u first. Okay, that's my order of the double integral. And then the next one here is from 0 to 2 pi in respect to v. Okay, but this is now a very simple integral right here for us to integrate. So it does take a few steps, and unfortunately my board is not spacious enough, so I'm leaving out all of the minor detailed steps like that. And so with a property that we have learned from the days we were doing the double integrals, then we can rewrite this integral here as one separate integral from 0 to pi for sine cubed u du. That's one separate integral in terms of u. And then we multiply with another integral for accumulating from 0 to 2 pi on the function cosine square of v dv. Okay, and we are allowed to do this simply because our function here is simply a product of two separate functions. One is of u and one is in terms of v, like that. All right, and then the calculation can just simply happen, which is easy for anyone to follow along and do each one of these independently. So the final answer here should come out being a 4 pi over 3, or 4/3 pi right here. And that's the answer that we have for this, the surface integral. All right, so that's how it's done right there. That's how we have managed and calculate a surface integral of a scalar function. Right, so what we have here was a surface integral. It's a double integral over a space surface S right here. It's a sphere, it's a unit sphere. That's our surface right here. And we take that accumulation together, accumulate it together with our scalar function x squared right there. All right. All right, so let me bring up a couple of why questions. Okay. The idea is that if you notice, if you have watched some of my earlier lessons, when I was explaining about a multiple integral, I tend to go into really in-depth and start out a lot of times prior to this lesson. I use double Riemann sums or triple Riemann sums to explain a lot about that. But now when it comes to this, I assume that my students or my viewers getting to this lesson here is already fluent enough. But now I want to explain a little bit about the why here is in the sense of, see, back to a surface area problem. Then we simply just accumulating all of the little ds, all of the little tiny sub-area units right here, accumulating in a double accumulation right there, and we get the total area. But now, when I'm saying why, I mean, why did we multiply? Why do we have to? I mean, is there a need? Is there an application? That's the idea. That's why I'm asking why. I'm bringing up to your curiosity right there, that question. Why do we multiply each of the ds right here with some scalar function value at f of x, at x, y, z? Why do we multiply like that? Okay? So think about it this way. Think about it this way. There are many occasions where you are given a surface. And this surface, this space surface here at every single point, it has a different temperature. The temperature as a function depends on coordinates point like that. So the temperature varies differently at every point on that surface. Okay? Or sometimes, and then so in that way right here, okay, we can average out. We can just find the average by accumulating, see, temperature at each point varies differently at each point, but each point is close enough with just a sub-area unit right here. So we multiply the temperature at each point with the sub-area units right at that instance, right at that point. And we accumulate all of that throughout the surface. Okay? And then we divide by the area of our surface right there. That gives us something like this. That gives us the average, okay, the average temperature on this entire surface. There are problems like that. Think about there's a copper or some kind of metal materials like that it's cold on one end and it's hotter, and it's not like immediately switch between cold and hot. It's cold and then it's starting gradually hotter, right? Depending on different areas of your surface like that. So we do a surface integral here to obtain the average temperature on that the surface material. Okay, on the surface of that material. That's one application of why we need to do this. Multiply each area unit with a scalar function. Okay, there are other applications out there. So again, why do we multiply each sub-area unit with a scalar value function? Think about, we got a surface, and now we're talking about the mass. Okay, it's a very thin surface, but in the end, it's so thin enough to the point that the thickness is neglectable. But at every point here, we got a different density, mass density function, which is varying depending on the different points x, y, and z on each different point on the surface. All right. And so mass density as a scalar function multiply simply with just the units area right there, because mass, now when we are neglecting, when I have already mentioned that, and we all agree that we're neglecting the thickness indicating volume of this thin thing, then in the end mass density is only dependent on the units area. So it's whatever grams or kilograms, right? The mass units per unit of area. So multiplying that and accumulating all of those So multiplying this gives you the mass at that particular sub-area unit. But now we need to accumulate all of the masses throughout the entire surface to get the total mass of your thin surface. It happens that way too. There are that kind of applications out there. And that, again, explains the reason why we need to sometimes, a lot of times actually, multiply the sub-area units with a scalar value function and do a double accumulation with that to produce to create what we have so-called a surface integral right here. All right, and so now I keep talking about some nice applications of that. In the end, after talking about some nice applications, and you have a whole world of applications of surface integrals out there to look for. And now in the end, if you look back, I kept talking about the video lesson where I talked about surface area. So now if you're looking back at this surface area formula right here, okay? This is surface area formulation. But think about it. In our understanding with integral at this point, S here can always be thought of as 1 times S. And we're accumulating that. So 1 here times S, this constant value 1 itself is already a scalar function of 3 variables. All right, and so that idea has already existed. That idea has already come around since your earlier learning, and now we just bring it back and put that together with our extended learning, right? To enforce our understanding. All right, and so you have seen the idea of surface integrals before this. All right. All right, and so now you are ready to arrive at that other type of surface integral. Now we're looking at surface integral of a vector field. So it's extremely important that you have already learned about what it is to be a surface integral of a scalar function. And now we advance over to learning about what a surface integral of a vector field is. All right, so needless to say, that at this point, in order to learn successfully what a surface integral of a vector field is, you need to also master your understanding about what a vector field is. Okay, and so and this work right here is specifically done with vector fields of 3-dimensional vector fields. Okay, and so now let me begin with the idea right here. Now you got a surface, and so agree with me at this point. Anyone can agree with me at this point that a surface going through space right here. You got so many points contained on that surface right here. Okay, and so now the vector field at any point, the idea now is to think about, we put this surface in a vector field. So at every point on this surface, there's a vector, there's a vector, there's a vector, there's a vector. Okay, vector pointing. Okay? You can think about either vector going through or going from that, or there could be the kind of vector field where every vector is hitting onto the surface of that surface right there. Okay, so that's why having a vector field, we put our surface here in a vector field. That's why at every point there's a vector acting on it. Okay, and so now, but just like that, again with that same idea. Okay, I'm talking about, we're starting with this surface area formula. So needless to say, you also need to already learn and master your skill in finding surface area of a space surface prior to this lesson right here, when we're looking at surface integral of a vector field. Okay, but now again, starting with our formulation, general formulation for a space surface area. Okay, then think about that. So now in our problem here, we pick a point. Let's say a point right here, and so yes, we are going to magnify that point into a subunit area, and that's here we call it, it's a ds. Okay, and so back in the days, right, with this ds right here, we're just simply accumulating all of the ds, and we get the total surface area. But now, okay, this is what we're doing. We're not only just accumulating the ds, the area units. We're not only just accumulating all of those. We are, before we accumulating those, this is what we do for each, right? So now I have to say for each ds, right? This is what we do. We will multiply Because the idea is like this. On each ds right here, on each ds, there's a vector from the vector field. On each ds, and now I'm drawing that very magnified version, so it may make you think that, hey, there are many vectors right here, so it's hard to choose, but the point is, right at one infinitesimally small point, you can still see that in a very extreme magnified version. Okay, it's a area unit. And so just assume that it's so small to the point that there's only one vector right there. Okay, so that only one vector is maybe like that. Okay, pointing out right there. So that's from the force, that's from the vector field. And then now each little units area right here, each little of the sub area units right here, there's also a vector that I so call the normal vector, being perpendicular with that. Okay, so my red version right here is the normal vector. Even though, I may not make it look precisely who's the normal one, who's being perpendicular and who's not. But this one here is from the vector field F, and this one here is from the normal vector. These are all vector. And I purposely use the unit normal vector. So the n right here is really the unit normal vector. All right, that's the idea right there. And so now back to what I was saying in the middle of saying right here. So for each of our sub area units right here, I am going to take the dot product between the vector that's existing right at that sub area unit. I'm taking the dot products between that vector and the units vector right at that spot as well. Okay. Of course, a dot product between any two vectors will give a scalar. But whatever you think of that, you don't need to get too far into that. Or that's just a brief reminder. Anytime taking a dot product will give you a scalar. We will get all to that idea later on. But right at this point, all I need you to understand is that what we do here on each of those sub area units, we take the dot products between the vector from the vector field F with the normal units vector. The units normal vector. And then that dot products there, I am going to multiply that with S. The reason I had to say a little bit, even though I didn't want you to think too far into that, okay? I don't need you to think too far into that for my audience at this point right here, but the reason I had to mention that a little bit, because in the end it's a scalar value, and it's going to be just fine to multiply that value without ds right here in the usual multiplication way, in the usual multiplicative way right there. All right. So that's what I do on each of these points, but think of each of these points as an infinitesimally small sub-area units. That's what it is. And so now in this way right here, so just like that idea we have seen previously when I was pointing out about the existence of a surface integral for scalar function. And here, now you got f dot n for each ds. And then you multiply f dot n with ds on each ds right here. But now we have infinitely many of those ds. So now we're going to take a double integral, or we take a double accumulation all over the entire surface S. All right, ladies and gentlemen, we call this setup right here. This is the surface integral. Okay, the surface integral of the field, and I mean the vector field for short, which is called a field, but it's really a vector field. F, all right, over the space surface S. That's what it is. All right, and so now you have, and in my style of teaching this, then surface integral is a subtopic of surface integral over a vector field in a vector field, or of a vector field, is always a subtopic of just our general discussion about all surface integrals out there. And so I assume that, and in my style, this surface integral over a vector field must always come after the learning about surface integral for a scalar function. And so I assume you have already seen my explanation for when I was explaining about surface integral for a scalar function. And so a lot of analogous arguments stays the same here. Okay? And again, as a reminder, this ds is exactly the same meaning, has the exact same meaning with the ds when I was showing up, when I was giving the explanation about the surface area, about how we calculate surface area. All right? And so now think about as a consequence of what I just said right here. Then now again with S, okay, parameterized with S being put in parameterization, being put in parametric form like that. So with the surface S parameterized by a given parameterization, by some given parameterization. Okay, then this is what we can do. And so, of course, there will be, we can also express S here as a surface, this surface S here as a function of two variables, but let's hold on to that topic or even put that as a one separate lesson right here. But here, let's just focus that to the understanding that S here is parametrically described. Okay, so that we can keep our study a little more narrow and focused here. So we just want to focus on those parametric surfaces. Okay, so that's why I'm saying now with S being parameterized, right, or with S parameterized by a given parameterization, or as a vector value function, two variables u comma v. All right, if that's so, then this is what we're doing. The first thing to keep in mind now is that since S is parameterized with some given, and I got to really highlight that word, some given parameterization, then with given parameterization for S right here, being some R of u comma v, right, then the normal, the units, this unit's normal vector, the way how we get that, it's done by, it's the vector R u cross RV as a vector, and we divide it by the magnitude because it needs to be a unit. Okay? So RU, the magnitude of RU cross RV. All right. So why are we having this formula? Okay. Quick explanation. So now that we have our surface here being parameterized by some vector value function, so I had prior to this lesson here a separate lesson to explain how we can construct parametric spacer surfaces. Okay, so in the end, we always going to have to end up with grids anyway. So each way of the grids, there are always two ways of doing the grids, right? And one way is corresponding to the u variable, and the other way is corresponding to the change in the v variables. Okay, so in the end, think about any of the sub-partition right here, then at any point, right? The RU, if these grids going in this way right here, if these grids going this way are corresponding to the u variable, and those other grids going in the other way corresponding to the v variable, then RU means the tangential vector, just the tangent vector. I didn't say anything about units. Okay, the tangent vector in the u direction, or corresponding to the u parameter. And then the RV right here is a tangent vector at that point on the surface in the direction corresponding to the v variable, to the v parameter. That's why taking the cross product, and think about it, these two vectors right here will define a small tangent plane. And so the normal vector must be perpendicular to the tangent plane right at that point. And so to find a normal vector, we simply take the cross product, okay? See, so this is RU and this is RV. Okay, so RU cross RV, all right, will give us a vector, a normal vector that points away from the surface. Okay, that's the way how we see it. It's the normal vector. Okay, I'm not saying that pointing down or pointing up. I'm not talking about that. I'm not talking about the direction of the vector, but the rule of thumb is that the vector always points away. The normal vector will always point away. After taking the cross product, okay, it will point away, and then the perpendicular, all right. And so now, in that way, right there, from that, right, But that nothing guarantees that it's a unit vector, and that's why we divide by the magnitude, and that gives you the unit normal vector. That's how we get the unit normal vector. So having a parameterization, we are able to come to getting the unit normal vector, and can eventually express all of this here as a final vector in terms of u comma v. Again, another vector in terms of u comma v. All right, and so now, on the other hand, as I keep reminding you, then ds here has the exact same meaning as that ds that I gave the explanation back in the lesson about calculating surface area. So ds can be re-expressed as the magnitude of RU cross RV. All right, with some dA. All right, so now with these two results, think about it this way. Our starting surface integral in the beginning being the vector of f from the vector field in dot product with the unit normal vector, okay, and then multiply with ds. But now working it out a little further, I can rewrite this integral as an integral over the surface S. Okay, f here can be expressed as f in terms of because every point in a vector field, every point x comma y comma z in a vector field can be expressed as a function r of u comma v. Okay, and then we take the dot products, but now this is going to be the dot product between. I can re-express that n right here, that capital N, as RU cross RV over the magnitude of RU cross RV. That's f dot n right here. All right, and then further, the dA right here, the ds here is all that magnitude of RU cross RV times dA. So I'm going to fit this in, okay? And it's all just the usual multiplication. So the magnitude of RU cross RV, okay, in absolute value and dA. All right. So this is, it's a little bit lengthy right now, but that's how we substitute things in. And so now in this way right here, think about the consequence. These magnitude as scalar values will get canceled. All right, so our surface integral now becomes, it's a surface integral, okay, for the vector field but being evaluated at the points defined parametrically, or of u comma v. So the vector field evaluated at each point parametrically or of u comma v, and then we take a dot product with after canceling this, we have a remaining vector being or u cross or v as a vector multiply with dA. All right, so it's a dot product still, and multiply with a dA expression. And now everything all of a sudden now expressed in terms of u and v right here. And so of course this now is the S represent the whole surface. Now is changed to just d right here, where d, okay, is a similar argument right here, the domain, okay, the domain of all u comma v pairs right there. All right, that's how we're doing it. And this formula right here will eventually give us access to the actual calculation. All right. So now we are ready for an example. All right, so this is our example right now. We want to evaluate in this example, example 2, we want to evaluate the surface integral f dot n over the surface S, where the f here is a vector field defined by minus y comma x comma 0, and S here is a surface that's have a given parameterization. So here we have a given parameterization. R of u comma v equals u for the first component, for the x components, v squared minus u, okay, for the y components, and u plus v for the z components. And then now we have a domain for our u and v parameters right here. So u changes value anywhere from 0 to 4, and v changes value anywhere from 0 to 3. So what we have here is simply some space surface with them, okay? And we're not required to see the actual graph of this, right? If you have any kind of technology with capability, with the graphing capability to graph a parametric surface right here, you are more than welcome to punch this in, and get the surface to have an idea of what that is, okay? So now, right? So to get into the problem itself, to get started with the problem, since we already had a parameterization given for our space surface right here, then f initially was given as a function, a vector value, a vector field of it's a three-dimensional vector field minus y, x comma 0, so minus y comma x comma 0. But remind yourself that r of v, right, r of u comma v was already defined as u for x, and then v squared minus u for y, and then u plus v for z right here. So now I'm going to take that value, okay, and substitute for the x here. I'm going to take that value because that's y, okay? I'm substituting that for the y value over here. And I'm going to take that, substituting for z anywhere I see the z, okay? And so in this way, the vector field will become minus v squared minus u, comma, u, comma, 0, which we can rewrite, which can be rewritten as the vector field in terms of two variables, okay, u minus v squared, comma, u, comma, 0. So that's our vector field with r of u comma v substituted in, okay. Now on the other hand, yes, we can easily calculate our RU. RU here will be 1 minus 1 and 1, because our vector value function in respect to u and v is here. So taking the derivative, the partial derivative of that in respect to u, it's 1. Partial derivative of this middle components in respect to u, that gives negative 1. That term goes to 0, and then that gives positive 1. And that's how I arrived at that r of u earlier. And so now, in that way, similarly, r of v, r sub v, is going to be, okay, 0 for the first component, 2v for the middle components, and just 1 for the third component. All right. So that's how I'm getting the two partial derivative vectors. Like that. These are the two tangent vectors, right, along the two different parameters. And so in that way, now let's take the cross product. Okay? The cross product here, RU cross RV, okay, is the determinants I, j, and k, right? And then we got RU placed here first, so 1, negative 1, 1, and then we got 0, 2v, and then 1 right here, and that's a v, by the way. Okay, and so expanding out this determinant, we're going to arrive at the normal vector, but not the unit's normal vector, just the normal vector here. It's going to be, okay, so in my calculation before this, so we got negative 1 minus 2v, okay, comma negative 1, comma 2v. All right. So that's what it is for our r cross v right here. And we don't even need to divide that by the normal, by the magnitude of that, okay? Because this is everything we need right here. We need the cross vector, the cross product vector. We need the vector field substituted r in. Okay, so now we are ready for the final setup of our integral, for our the surface integral. So the surface integral in the beginning, over that S, that field, over that surface S right here, of F dot N. Okay. That can be rewritten as a surface integral, okay, or a double integral over the region D being the domain of U and V. And then now F is this, so I'm going to just write it down for now. I'm going to have U minus V square, comma, U, comma, 0, okay, but in dot products, right, with this normal vector that we have just calculated, minus 1, minus 2, V, comma, negative 1, comma, 2V. All right, and then everything here is multiplied with a dA. All right, so that's how it's done right here. And now this will give us some the final access, right? The actual access to the real calculation. I'm running out of space, and I don't want to erase the beginning problem over there. So I'm going to erase some part of the work that we've had up here. All right, so to continue with that work right here, our next integral here I will have, okay, I will decide to go for, so this components in dot product with that gives me, okay, V square minus U times 1 plus 2V right there. So the negative sign here, after multiply together with that difference, it switched the order, so making it V square minus U instead of U minus V square. And then now all that become a plus. So a little bit of algebra like that. Okay, so that's the first component in the dot product. And now U times a negative 1. Okay, U times negative 1. So making it negative or minus U. And then 0 times 2V, it's just a 0 out. So we got that, completes our integrand, right? And so now, in my style, I like integrating in respect to the letter U first. So U is going from 0 to 4. Okay, so now my dA is du dV. So V changes from 0 to 3. And that's how I complete my integral setup right there for that. And then with this integral right here, we are ready to obtain a final answer. And then anyone can easily calculate this as a double integral. And then the domain here is simply that U changes from 0 to 4 and V changes from 0 to 3. And that's how I got it set up right here. So calculation came out for me being a positive 78 for this integral over here. Okay, and then for anyone viewing this lesson, of course, it should be extremely easy that you go through the steps to do a double integral over this rectangular region right there. So needless for me to show the written steps for that. All right. All right, and so now at this point we are going to answer we are going to look at the reason why we have to study about those surface integrals here. So at this point in our learning, a surface integral, as a general formulation, it's a double integral over a surface S right here with and specifically I'm looking at the reason why we have to study of surface integrals for a vector field. And so we have a vector field S, and what we've been doing is the vector field S, every vector in the vector field F is taking the dot product, it's taking it as a dot product with the normal vector at every point, and then we multiply with the ds quantity, and then we're accumulating over the entire surface integral. So there are many applications out there. Now, in the application that's closest to my the work right here personally, and that's the one that I work with most often, then it's proven that, think about on a surface right here, in a 3D surface right here, okay? Then the amount of heat flows that can flow through that surface. So a vector field is pretty much anything that's indicating a flow. Like that. So think about heat flow right here. And so through at any point right here, it is proven, and this is a little bit, we have to bring in the physics understanding right here, but heat flow can be, now if the heat at any point is a function of x comma y comma z, x comma y comma z in space right here, then so at least on that through that surface right here, then the rate of flow the rate of flow as a, let's call that a field u right here. A vector field u of x comma y comma z is proven in physics that it's going to be some constant multiplied with the gradient of the heat function. Okay, and so in that way right here, measuring the heat flow, the total amount of heat flow, we are going to do the total amount of heat flowing through that surface right here. And we're looking at this total surface where we're doing the dot product between our, and so this gradient, this vector field right here is understood as the amount of heat flow per unit of area, okay, per unit of area and per time, like that. And so now we're accumulating all of that. Right? So it's a rate of heat flow per unit of per time and then per unit of area, and then we're going to accumulate. We take the dot product with the normal vector, okay, at every point like that. Okay, so there's a normal vector at every point, and then we multiply that with the infinitesimally small ds area sub area sections right there, and accumulating all of that, we have the total amount of heat, right, per amount of time. Okay, and then that flows through this entire surface right there. All right, so that's one example right there that we can, one amount of the applications that we can measure out there. Now another example we can quickly see right here is that, think about a surface and water is flowing through. Okay, water is flowing through that surface right here at some velocity v as a vector field right here, because at every, think about water as a fluid, then at every point really it has a different velocity, and so flowing through that, right, then the velocity field right here is going to be understood, this vector field here is understood as the velocity, how much flow per unit of time, but and then velocity dot with the normal vector right here is indicating the amount of flow per unit of area, and then we're accumulating all of that, and that gets us right here a total rate of flow. Okay. Through the entire S per unit of time. Time could be per second or per meter. Okay, and so F here is a vector field of 3 dimensions. Okay. All right. So those are a few different applications out there, and there are a limitless number of applications for taking a surface integral right here. All right. And so at this point, after having some thorough look at some of the examples that we have throughout the examples we have done right here, I would like to make a couple of remarks right here. And so the number one thing, a surface integral of a vector field is also referred to as the flux integral. The flux integral, because it's indicating, as I have explained earlier throughout the applications that I pointed out. Of course, we didn't get into any of those applications, but the idea is the amount, we want to measure the amount of vectors that flows through, and that's why it's a lot of times it's called a flux integral. Okay, So that's one remark right there to keep in mind. And then in the end, if you're looking at a flux integral where it's the integrand itself is in the form of the vector from the vector field in the dot product with the normal vector at any point, and then we're accumulating all of that. And so this component here is easy to understand. That's from the usual the ds, the subpartition of the area, okay, that we usually know from the calculating area of a surface. But in the end, this quantity right here, even though it's vectors and vectors, but in the end it's a dot product between vector, and dot products will come out being a scalar. Dot product will come out being a scalar. Okay, and then of course these are all functions of the three variables. So taking the dot product, it's going to come out being a scalar function. And so in the end, even though we moved on to a flux integral or a surface integral for a vector field, but in the end, okay, a flux integral. Okay. A flux integral is also a surface integral of a scalar function. So it's worth to note that. All right. So a flux integral is also a surface integral of a scalar function. But the way we approach that is slightly different. Okay, and so that's what we need to know about what the surface integral is. All right, and so now if we're looking back at the examples that we've done earlier, there's this idea behind the scene that we didn't look very thoroughly, but so now let's give it a closer look so that later on when we bring this into, when we get into some further concepts, some later concepts that heavily involves the surface integrals, then we will move on. We will move on a lot more smoothly. Okay, but the idea deep behind the scene, one key concept behind the scene for any of these surfaces, they have to be. So any of these surfaces that we're taking the integrals over, they have to be an oriented, okay, an oriented surface. So let's try to understand what an oriented surface is all about. So now that we're looking at surfaces and we're taking accumulation over surfaces, and you've learned the idea, you've learned the steps, how you've done that. But now if you're looking at any surface, here's a nature. It's just about, so when we're talking about an oriented surface, we're studying about a nature of a surface right here. So there are those surfaces where permanently, see, let's say I'm drawing a surface like this, like a piece of paper that I put in front of you right here. This is a surface in space. So an oriented surface, but first of all, think about this surface right here. There are those surfaces that it has a property that it permanently remains with two distinct sides. So this surface of mine right here, it got one side it got one side and it got the other side right here. So just like this, the surface I'm drawing right here has two distinct sides. So the first term I want to introduce is an orientable. An orientable surface. We have two sides, okay, at any points on the surface. Okay, so pick that point right here. There's a side, and there's at that same point there's a side pointing out. But then, how exactly do we categorize the point, the sides, and which side and which side? And it, of course, in a 3D space where it can be pointing all over, then the side now is, to get a little more precise, each side of a surface is determined by a set of normal vector. So the idea of an orientable surface now is that at every point there will be two unique normal vectors. So there's, if you can call one normal vector over here coming out as a normal vector 1. And then the other vector over here will have to be the opposite one for here. So n2, but n2 is exactly the opposite of n1. So at every point, So a surface being orientable, if at every point right here we can find two distinct normal vectors. So it's the same way as saying two, or actually opposites, okay, two opposite normal vectors. All right, normal vectors at any point. Okay. All right, so it will have two sides, right, at any point, or it has, more precisely, it has two opposite normal vectors at any point. And that's what it means by an orientable surface. So does that mean there are non-orientable surfaces out there? Yes, there are. A classic example is this. All right, so right here is a classic example for a non-orientable surface right here. So think about the way how this strip looks right here. So right now, if we place a normal vector right here at any point here, the normal vector will point outward, and then it point up this way when it twists here, and then all of a sudden when it starts getting to these area, it's gonna point inside. So really, there are not really a two sides. So really, which side is a one side for this strip right here? There isn't. There really isn't one side. It's all just one side, even though it looks like a two side right here. See, this side is actually the same as that side, because when we're going further and we're going further, it twists back in here, and then it goes in the inside, but then, okay, it goes in the inside, and then at some point, it's gonna swing back, right? That inside part is gonna go underneath this, and then it goes around behind this picture right here, but then it's gonna loop back and come back to this point. So it's all gonna be really just one side right here, and this is an example where it's a non-orientable the surface right here. It's a surface, but it's a non-orientable surface because we cannot decide which side is, we cannot decide which one side right here. All right. And so, back on the picture that I've set right here, then so an orientable surface will always have two sides that we can pick. So, and the point of having a two sides is we can pick one side. And so now, so in that way, an oriented surface, okay, means so an oriented surface means a surface where a side, one side or a side is already determined. Okay, it's already determined. Okay, one side is already determined. And so this is what you usually hear. I tend not to use that term too often, but usually the side that people determine. So really on a surface right here, you can pick that side to be your chosen one. Determined means we can pick one side. So the side that you have determined to be your side, indicating where it's facing, that side right there, people usually call it as the positive side, even though I don't use that term that often. But sometimes, I may use that as well. So the positive term, the positive side, okay? And then so once you have determined which side is the positive side, automatically the opposite side will be the negative side, okay? So at any point, there are, again, the idea now is an orientable surface. At any point, there are two set of vectors, and to be precise, at any point, there are two vectors, two normal vectors, pointing to the two different different directions of facing like that. And so, and once we picked one side, and basically picking one side here means we pick a whole set of normal vectors, okay? And then any textbook that you're taking has a precise definition of what it means by a one side of that. One side really is just a whole set of continuously varying normal vectors here. But once we have determined one side, right, that's called our surface there is oriented, meaning we already decided one side. Okay, and then that side that we decide it's called a positive side. Okay, and then the opposite side has to be the just the opposite set of normal vectors. And so in that way, consequently, in the way how I see it, this is where many textbook authors have so many different interpretations, including the way how I interpret that to my students right here. But to keep it simple for my students, I've always been teaching that admittedly at this point over here that you've learned any surface has a parameterization. Any surface has a parameterization. So this surface S right here, let's say it comes with a parameterization. Okay, and for each surface right here, there could be even multiple parameterization. So the idea now is that depending on whichever parameterization that you come up with, then normally we choose the normal vector at any point, right? At any point, we choose the normal vector to be and I'm talking about when your surface is parameterized, then it's always consistent that the normal vector at any point, there's a naturally induced normal vector. It's being found by the tangent vector R of u cross with R of v, and then when we want to take that as a unit normal vector, so we divide it by the magnitude of the cross product of Ru and Rv. And so this normal vector right here, I'm not saying that it's always the case that it's pointing up or pointing down, but depending on your parameterization, then the one that comes out from this cross product over its magnitude of the cross product, and the cross product here involves Ru, the tangent vector. So think about at any R right here, we got a tangent vector Ru going this way, and then there's an Rv going the other way. So the cross product gives a vector pointing up. But some other parameterization, it may, after taking this, it gives you that same point, give you a vector pointing down. And so we choose that default one to be, this is a lot of time people tend to call this natural one. It's the positive normal vector, and that defines okay, and then that defines and then whichever that comes in the opposite way, that defines the negative, the side right there. So the set of all positive normal vectors based on that's induced from your parameterization, that defines the positive side, the positive normal vectors. Okay, and then the opposite side, the other side is going to be the negative side right there of your vector right there. But then as we go further, we will further into going into the different problems. I will point out different ways, different conventions of how people choose a side to be called a positive side. And so, but the idea, the bottom line is, we're always going to have to make sure that the parameterization is consistent with the side that we choose. Sometimes we purposely want to choose a side. Say, for example, a surface pointing up like this. Sometimes we purposely want to choose a side that's going up like this, where all the vectors pointing up like this, the normal vector is pointing up. If we want to purposely choose that side to be the positive side, then we have to pick a parameterization that's consistent with this nature. All right, so that's the idea right there. So, well, there are multiple. The bottom line, there are multiple parameterizations. And so if we just strictly follow with the multiple, with the whatever parameterizations we are given, then we just stay with this and consider that as our positive side of the surface, and then from there our surface is oriented. Okay, but then in some cases, there are some cases out there before we look into the parameterization, before we have a parameterization, we already have a decision that, hey, let's pick the upside right here. Or, you know, if the surface is pointing to some right-hand side, and we're going to say, hey, let's pick that side. And think about picking that side means, picking a side means it's the side that when we place our eyes, another way of explaining it, if we place our eyes looking at it, then those normal vectors are pointing out at us right there. Okay? Like when I'm looking at this surface right here, there's one side out here and then this side right here. So if I'm looking straight at that, right, then I can sometimes purposely choose this side where I'm looking at that as a positive side, right? And that's the idea right there. And then, but if we choose that side where it's facing us being the positive side, and make sure we have to choose the parameterization that's consistent based on this observation right there, based on this formula right there. And so that's the idea of how we choose an orientation of our surface right there. Okay.